Hi, everyone. For those in the room who don't know me very well, I'm Melissa Green. I am an affiliated faculty here at SAFL. I'm in the Aerospace Engineering and Mechanics department, and I may be unfamiliar to some in the seminar series because I teach at this time this semester, so I haven't been able to come to many of the seminars, but I'm very excited to be able to introduce Dr. Keith Mord for our seminar today. Keith received a BS in Aerospace Engineering and a BA in Physics at the University of Virginia in 2004, and then I don't know what that was. And then also received his PhD there in 2010. From 2010 to 2013, he was a postdoctoral research associate and a lecturer in the Mechanical and Aerospace Engineering department at Princeton, which is where he and I we did not technically overlap, but where our friendship and collaboration had its seeds. His research interests are in bio-inspired propulsion, unsteady aerodynamics, and fluid structure interaction. And he is the lead PI of a new ONR Muri grant that was funded within the last 6 months or so. On the hydrodynamics of fish schooling. So not necessarily just the bio-inspired propulsion, but also the interactions with multiple bodies and the collective motion therein. He was also a participant, a PI on the previous Muri that was on just non-traditional propulsion. So fish like swimming for fast and efficient motion, I believe that was titled. And he also previously received an NSF Career Award for fluid dynamic interactions among schooling swimmers. So as I indicated, I've known Keith for a number of years. I know his work is excellent, and especially with the recent experience he has in leading Muri teams, which are necessarily strongly interdisciplinary. I thought he would give a fantastic talk for the SAFL audience, and I'm really excited to hand it off to you. So thanks for coming.
Well, thank you so much. Thank you so much, Melissa, for the nice kind of introduction. It's been great to be here and to get a chance to see the SAFL facilities here. You really have some amazing, unique capabilities. It's fantastic. I'm already thinking of project ideas that we can start to do. I have had a wonderful day kind of meeting everybody and hearing about all the amazing research happening here. So I'm excited to hear more of it a little bit later today. But I'm going to be talking today about the hydrodynamics of fish schooling. As Melissa mentioned, this is a project that is a Muri project that we have officially got started in last September. So it's been about 7 months since that project has begun. So we're still in the beginning stages, but I think we got a lot of cool things generally to talk about. So yeah, we'll see if we get this working. Okay. It's good. It's good. It's technical difficulty fixed. So, okay. Yeah, it probably is Zoom's fault, I'm pretty sure. As I mentioned for this ONR Muri project, as Melissa mentioned for this ONR Muri project, it's a multidisciplinary team involved. So we have 6 PIs, myself being one of them included. So I'm leading the project. We have Hilary Bartsmith, Haibo Dong, and Dan Quinn from the University of Virginia. We have Radhika Nagpal from Princeton University and George Lauder from Harvard University. As far as the work that I'm going to be talking about today, these are the kind of students and postdocs involved in this work. Although I guess Chung is no longer a student or postdoc anymore. He's now moved on as a faculty member at University of Iowa State. But otherwise, these are students and postdocs in my lab. And I want to point out 2 students in particular here. So there is Pedro Armand and Tianjin Han. So these 2 students are senior students. And so they should be graduating sometime this summer. And they are, I'm shamelessly putting in a plug, right? They are looking for postdoc positions, but they are fantastic. And they both have done fantastic work. And a majority of the work I'm going to be talking about today is coming from one of the 2 of them. Pedro is doing basically all the experiments I'm going to show from my team. And Tianjin is doing the numerical work. So we have a kind of a 50-50 split in that regard. So generally in my lab, I do work in unsteady flows, much like Melissa does. And we see unsteady flows all throughout nature and the engineering world. So we see this, of course, in animal locomotion. We see this in fish schools, which I'll be talking about more today. We see it in mammal locomotion. We see this in bird flight. We see this in bio-inspired applications, such as the biorobotic swimmer Tunabot, which we'll be talking about a little bit today. We have another project that's funded through the Department of Energy, ARPA-E to be more exact, looking at oscillating foil hydrokinetic turbines. So these are renewable energy devices based on bio-inspired principles. But you see unsteady flows not only in those kinds of applications, but also in more conventional engineering applications, such as in rotorcraft, vertical axis wind turbines. You see this in interactions of horizontal axis wind turbines with the atmospheric boundary layer. I know there's work happening along those lines here. You see this in geophysical flows, like in the cloud pattern here around Guadalupe Island. You see this infamously in the Tacoma Narrows Bridge disaster as well. So we see unsteady flows really all throughout nature and the engineering world. And we're going to be focusing more on these bio-inspired applications, in particular, fish swimming robots and fish swimming in general. And that's going to be our kind of focus today. So one area that we've been working on in a while is this idea of fish-inspired robots. And you might ask yourself, well, why are you interested in doing that? And so really the answer comes that this is a way to develop the next generation of underwater vehicle technology. And we look at this kind of as a package deal. A lot of attributes can be improved by considering bio-inspired devices. If we look at classical torpedo-styled rotary propeller-based vehicles, we can start to compare those vehicles to biological systems or bio-inspired systems. We see that they have kind of comparable swimming speeds, they have comparable efficiencies. Maybe we could do a little bit better on the biological side, but they start to see more dramatic differences when we're looking at the maneuverability and agility characteristics. So the turning radii are much smaller in biological systems, much faster turning rates. And the Navy particularly likes the idea of the noise signature involved with these robots as well. If you swim a robot like a fish, you can actually achieve fish-like noise signatures, which makes it very difficult to detect from other background noise in the ocean, which are a lot of times fish. And so this offers a sort of acoustic stealth as well, kind of built into the system. So we've looked at these kind of isolated swimmer problems to try to understand fish locomotion for years. There's still much more to be done in that area on just solitary fish and solitary bio-inspired robots. But what we're interested in doing now is moving to this idea of groups of robots or schools of bio-inspired robots. And we're interested in doing this for two reasons. One reason is that we know we can derive hydrodynamic benefits by schooling. We know that the robots can save energy by swimming together rather than by themselves. We also know that we can now, with a group of swimmers, perform novel distributed tasks. And so this opens up possibilities of what these robots can do. And so we're very interested in these kinds of ideas. So I got to start with a little biological inspiration. So this is a fish school, of course. I just find this mesmerizing to watch, to see kind of the synchronization, the kind of coordination among these fish is just beautiful. Fish school for many reasons. They do this for protection against predators. They do this for socialization reasons. They do this to enhance their foraging, but they also do this to save energy. And it's this latter point that we know the least about. Our understanding of the hydrodynamic interactions in fish schools is still very primitive. So the goal of our MURI project is to really discover and to then demonstrate the hydrodynamic principles of high-speed, high-efficiency schooling, excuse me. So what we do know is that there are many variables and mechanisms involved in the hydrodynamic interactions of fish schools. Many of these are derived from studies that are two-dimensional studies of just a pair of swimmers. But what we've figured out so far is that there are a lot of variables and mechanisms at play. So the organization, or essentially the relative spacing between individuals in a school, plays a role. The choice of their body kinematics or their body deformations plays a role in terms of their performance characteristics. We know that there is synchronization aspects between two fish nearby. If they are in phase with each other or out of phase with each other, that alters their hydrodynamic interactions as well. We know that there are vortex body mechanisms where a leader fish will shed a vortex wake and a follower fish can extract energy from that wake. We know that wake instabilities can also play a role to break down those coherent vortex streets and to make it more difficult to extract useful energy from just a distributed vorticity field. We know that there are direct body-to-body flow interactions that also occur in fish schools. And we know that there are these fluid-mediated forces, forces that kind of push and pull swimmers around inside a school. So what we don't know is really how these mechanisms interplay when we start to move to large schools, so more beyond 2 swimmers, when we start to move to 3-dimensional arrangements of swimmers, when we start to move to 3-dimensional swimmers, and we start to move to swimmers that are flexible swimmers. And so these are kind of the avenues that we are progressing throughout the Muri project to better understand what's happening in real fish schools and in biorobotic fish schools. We have three kind of key questions that we're trying to resolve, 3 unresolved questions. The first is, what are energetically optimal, speed enhancing, and or stable 3-dimensional schooling states? The second is, do real fish schools actually exploit those hydrodynamics? Are they taking advantage of what we learn in these kind of idealized or engineered scenarios? And the last one is, how is coordinated, stable, and high-performance schooling achieved through the fusion of hydrodynamic principles and control? So to answer these questions, I've assembled the Muri team that you see here that I mentioned before. And we're kind of categorized into 3 major areas: fundamental hydrodynamics, biological hydrodynamics, and biorobotic hydrodynamics. So for myself, I do work on hydrofoil interactions using both medium fidelity simulations and experiments. Haibo Dong does high fidelity simulations, immersed boundary methods, where he does hydrofoil interactions, but also things that are more fish-like swimmers. George Latter, several of you may know George. George's a fish biologist, does some fantastic hydrodynamic experiments on real fish. Dan Quinn sits somewhere between the fundamentals and biorobotics. He does work on hydrofoil experiments as well as what we're going to describe as semi-tethered biorobotic experiments. So things that are not quite free swimming, but are not completely simplified as hydrofoils either. Hilary Bart-Smith works in high-performance biorobotic platforms, and Radhika Nagpal works in biorobotic schooling control. And so the basic research process that we're trying to follow is to kind of discover the basic or fundamental principles using very simple and idealized systems in the fundamental hydrodynamics, and then to ever increase the kind of complexity and refine kind of our hypotheses along the way as we push out those salient features to tests in the actual fish and tests and demonstrations with the actual robots. And so what we learn from those studies, we're going to feed back into the fundamental hydrodynamics and kind of restart that process again. So I want to start off talking about a few results from the team at large. And so this is work from George's team. And so George is the biologist on the team. And it's actually, I said at the beginning that fish save energy while schooling. So is that really true? Do we actually know the answer to that? Right? The answer is no, we actually did not know the answer to that 3 months ago. So George has helped us fill in this gap and to be able to answer this question. It's actually quite extraordinary because everything that, I had learned kind of just in passing was that, sure, birds fly in a flock, they save energy, right? Fish swim in a school, sure, they save energy. Seems to make sense. But if you actually dig into the literature on this, there are no direct measurements of energy consumption in bird flocks or in fish schools. What they do instead is they'll do measurements, indirect measurements of energy consumption. They'll look at flapping frequencies, they will look at tailbeat frequencies, they'll look at heart rates, and they'll say if your heart rate is lower, your frequency is lower, then you're saving energy. Well, the problem is that that correlation is good sometimes, but is not always correct. In fact, the gold standard to measure energy consumption in animals is to use a respirometer to measure oxygen consumption and to get direct energetic measurements on these animals. That has not been done in bird flocks or fish schools. So George decided to be able to do this. So yeah, none of these measurements are found in literature. You cannot actually get this information until now. It only took George 3 months. So George has this facility here. This is a little test flume. This is for actually fish swimming in here. And this is a fully enclosed, encased tank. And so he measures the oxygen consumption coming in and out of this tank. They do these very precise measurements to be able to get this very accurately. He's done this with these giant Danio fish. He's done a school size of about 8 in particular. And they can really change the speed range quite dramatically for these fish from 0.25 up to 8 body lengths per second, which is really extraordinary. I mean, most fish studies won't go anywhere near 8 body lengths per second. They might be pushing 3 body lengths per second, perhaps. So it's quite extraordinary speed range for biological literature. They measure with 2 cameras the kinematic motions as well. So George can actually test out whether this kind of idea of using these kinematic proxies as energy consumption is a good metric or not. Yeah. See? Thank you. Thanks for taking care of that. So in the interest of time, I'm just going to show you kind of the major takeaway here from George. On the vertical axis here, we have a measurement of energy. So this is the total cost of transport. This is the energy it takes for the fish to swim a given distance per unit mass of the fish. On the x-axis is their speed in body lengths per second. The blue curve here is for an individual fish in that respirometer flow channel. And the green here is for a fish school with the 8 swimmers in this fish school. You can see very clearly that it costs about half the amount of energy to swim in the school at these high speeds compared to swimming by yourself. Right? So this is the first time there have been any direct energetic measurements. So fish really do save energy. What's even more striking, I'm not going to show you the actual data here, but George has found that he put in a grid as well and introduced essentially grid turbulence into the channel. And the fish, the difference in the school versus the individual was even more dramatic. And so an individual swimming in a turbulent flow spent 4 to 5 times more energy than the school swimming in that same turbulent flow. And so there is a lot of benefits to be had by actually swimming and taking advantage of schooling. By looking at the kinematics from those videos, he's found that it's actually, there's very little change in the tailbeat frequency, very little change in the amplitude of motion and the kinematics in general. And so kinematics really are not a reliable indicator of energy consumption. And you can't go on that alone to say that there's an energetic savings. And lastly, just a point that he has here is that this kind of cost of transport is some of the lowest measured in the literature on aquatic animals. So this really kind of sets the stage. Yes, please. They change the flow speed and this fish will swim to keep up. It's like being on a treadmill and they crank up the speed and so the fish just kind of keep up. Yeah, it's a good question. And there is a very long time span process to get these kinds of measurements because the fish have to acclimate to the actual channel itself. So they sit in the channel for, I think it's like 20 hours before they ever even start their measurement campaign. And then they measure oxygen consumption for another 20 hours beyond that to get the full recovery of the animals. It's quite detailed measurements to get that precisely. So this really sets the stage to say, real fish, when they swim in the school, they do save energy. They save a significant amount of energy. They save, on the low end, they save half the energy to swim, or maybe even higher if they're swimming in more turbulent environments, right? So they save an enormous amount of energy there. Now it's kind of our job to try to figure out, well, how can we replicate that in biorobots? How can we save energy on that order? What's happening in terms of the hydrodynamics? So we're really interested in this kind of idea of applying these kinds of savings to biorobots. So I mentioned that there's the 2 teams, Hillary's team and Radica's team, that have 2 different platforms. Here on the left are the Tunabot robots from Hillary's team. There's no control happening here. These are high performance robots. They swim very fast. They swim with, this is real time, 8 hertz or so frequencies, swim at 8 body lengths per second. They're kind of being suspended by some lines there. You can see the interactions are very unstable, right? They're kind of moving around a lot, especially when they're getting in the wake interaction there. Blue Swarm robots over here are from Radica's team. These are not high performance robots, but she's been focusing on school level control instead. And so they use localized sensing. They have onboard vision They can see the other robots and perceive the other robots, and they do decentralized control. So this isn't using kind of a camera system out of the water to do control. This is all onboard the actual robots. So they can actually do milling behaviors, aggregation, dispersion, kind of common behaviors seen in fish schools. And so she's really introducing this idea of school level control without the performance. But what we want to do is bring these two pieces together to get the next version of these platforms, the kind of hybrid robots that brings together high performance and schooling level control, so we could test out and demonstrate our principles at high speeds and be able to actually control what's happening there. So from the fundamental hydrodynamics perspective, our kind of sub-team is focused on trying to go from really simple and idealized systems, understand and uncover the basic kind of principles of schooling there, and then progressively increase the complexity and fidelity towards doing biorobotic experiments and doing experiments with real fish. So today you're going to see some work that I'm going to talk about that's focused more on the simple side of things, but hopefully uncovering some really interesting principles. So I'll be talking about the work from my team here. So we're going to focus on these hydrofoil experiments and hydrofoil simulations, focusing on the idea of stability and performance. So I have to get some variables out of the way so we don't have to keep talking about them. So this is going to hopefully do that. If you're a fish swimming, you can imagine this fish is going to oscillate its tail with some flapping frequency F. It's going to generate a vortex wake behind it with some wake width or amplitude A. This is going to propel the fish forward with some speed U. And there's a typical length scale you could talk about for the fish. It could be the whole body length. Typically, we're going to talk about just the chord length of, let's say, the fin of the fish. And when we're talking about hydrofoil studies, we really are thinking about those hydrofoils as being a model of just the fish fin by itself, and we're kind of neglecting the effects of the body. So we try to simplify things as much as we can. We can define different dimensionless numbers. We can think of these as kind of dimensionless frequencies, the Struhal number, the reduced frequency. We have the dimensionless amplitude. We're going to talk about thrust coefficient. And so we can take the mean thrust of a swimmer and normalize it by its added mass thrust to define the thrust coefficient. Or we can do it in the more classical way and use dynamic pressure. And there's a kind of simple relationship between the two. More often than not, we're going to talk about this normalized thrust, which is the mean thrust for a swimmer in a school compared to the mean thrust for a swimmer by itself. And so if this value is greater than 1, then there's a thrust benefit to schooling. If it's less than 1, there's a detriment or a degradation in thrust production. It also takes power to swim. You have to put in power into the fluid in order to propel yourself forward. So we're going to talk about a power coefficient. That's the mean power divided by the added mass power. Or we can use dynamic pressure. Simple relationship between the two, and more often than not, we'll talk about normalized power in schooling problems. If we're talking about the efficiency, it's simply the thrust and the ratio of the thrust and power coefficient. Using either normalization gives you the same result. And we'll talk about a normalized efficiency as well in the same way. So when that's greater than 1, you're doing better by schooling, you're more efficient. And if it's less than 1, you're going to be doing worse than if you're swimming by yourself. So I want to start off with some experiments that have now been done a bit of time ago, but they kind of set the stage, I think, nicely to understand the stability of formations. So in these experiments, these were done in our water channel over at Lehigh. We took 2 foils, we put them between a splitter plate and a surface plate here. And what we were looking at was actually varying the arrangement or the formation of these 2 foils relative to each other. We called one the leader, one the follower, and we put the follower at all these different grid points that you see here. And in fact, we have an extended domain that goes probably off the screen here somewhere. I'm going to show some measurements from that came out of a reviewer comment that they wanted to see more. So I didn't update the schematic yet, but we do have an extended domain too. What we were looking at mostly was the interaction forces between the leader and the follower. And so we measured the forces here, and we also measured the performance characteristics at the same time. So importantly, we fixed the phase relationship between these to just be one phase relationship. So these are operating out of phase with each other. And the Reynolds number is fixed. It's only 10,000. The Struhal reduced frequency and dimensionless amplitude are chosen here to maximize the efficiency for an isolated swimmer. So we didn't change those in this study. Mostly just change the positions here. On the output side, like I said, we're trying to figure out those interaction forces, and we talk about them as in terms of relative thrust and relative lift. And when we're thinking about performance, instead of talking about the thrust coefficient for the leader or follower by itself, we add those together to talk about a collective thrust and a collective power and a collective efficiency. And so it just helps us more easily look at the data as a whole group rather than an individual. So from that kind of campaign, it took, it's only one click away on a slide, but it takes a very long time to gather all that data, especially with this is our extended domain here. What we're plotting here is what we describe as a force map. And you can think of these lines here as being force lines, and they behave in a lot of ways like streamlines. But the way you want to interpret this plot is that you have a leader located here at 0, 0, and then, or the leading edge is at 0, 0. This is actually showing the real amplitude of motion for the leader. And any point you could pick in this field, you can imagine if the follower is sitting there, this represents the direction that the hydrodynamic forces would be pushing or pulling that individual. So if the follower is sitting here, you would feel forces kind of pushing it upward. If the follower is sitting here, you'd feel forces pulling it down towards the leader, and so forth. So what we see in here in this force map is that there's some really interesting critical points that show up in the flow. We see, for instance, this point, which is really exciting. This is essentially a sink. And in this sink, you could imagine if the follower is sitting at that particular location and it gets perturbed away from the leader, there are hydrodynamic forces that arise that actually pull it back to that equilibrium position. And if the follower gets closer to the leader, the forces push it away from the leader. And if it gets perturbed upstream or downstream, there are restorative forces to bring it back. And so this represents a two-dimensional stable formation that if the follower is swimming with an out-of-phase synchronization and it's around the side-by-side position, it'll get pulled into that particular position with no control at all, right? So it's happening purely by the hydrodynamic forces alone, and we can think of this as a cohesive force kind of pulling a school together into this particular side-by-side formation. There are other interesting points in this as well. There are these blue points here, which are essentially saddle points. And so you can think of these as being one-dimensionally stable. So along one axis here, for instance, in the streamwise dimension, this is stable. The two force vectors point towards the point. But in the cross-stream dimension, it's unstable, and it pushes it away from that point. And then we have some source points here, which are two-dimensionally unstable. So we like to think of this as really an opportunity that maybe we can actually be clever with the physics here. And instead of having a very sophisticated controller in order to achieve a certain formation and to gain a performance benefit, maybe we can design the physics to do a lot of that heavy lifting for us. And maybe we can have a very simple controller to kind of make sure that things stay in place. Maybe that means we're going to do potentially sparse sensing and save power on board for our battery and save power for swimming. Maybe that means we have cheap sensors or cheap control boards or very primitive control laws in order to be able to achieve a formation. Achieving a formation that's a stable formation is way simpler than trying to achieve one that's unstable. So we think of this really as an opportunity to more easily get to the point of demonstrating formation swimming where we can actually achieve a performance benefit. Now, there's one complication here. This was done for an experiment where we have foils fixed in place. We flap, 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 take some data. We change the position and do that again and rinse and repeat. But what happens if we allow there to be the actual kind of dynamic motion between these foils? Does that disrupt the stability landscape? Does this all kind of go away when that's the case? So to start to answer that question, we first turn to our in-house potential flow solver. So this is our boundary element method. And so this is a classic panel method. We use source and doublet panels distributed over the body and doublet panels distributed over any free shear layers to model these unsteady flow problems. We have a 2D and a 3D solver. We can do free swimming. We can do some leading edge separation. We have a boundary layer solver. We've done fluid structure interaction with this before. So a lot of bells and whistles kind of added on to that to make it work for different problems. Here's a three-dimensional simulation of this out-of-phase side-by-side arrangement, just showing some of the wake evolution happening there. And throughout all the problems that we've worked on with this, we always start with some validation and make sure that we're getting the right thing. This is a medium fidelity method, right? So we're neglecting some of the physics. We got to make sure that we're getting things right. And if not, we got to make sure we have a model that does it. So for schooling problems, and particularly in this kind of inline case, we've looked at this extensively, compared our flow fields produced by our solver to PIV experiments and to force data as well, and we get good agreement between the two. So we decided to check out this side-by-side arrangement, and we tasked our potential flow solver with this. So these two foils are pitching, and the kind of translational motion in the vertical dimension and streamwise is just solved through the equations of motion. There's no control being applied here at all. We started them close to the side-by-side position, and you'll see that over time they're going to settle into this perfectly side-by-side position, just as the constrained foil measurements had shown us. So introducing this kind of dynamic recoil motion, you can see they have a slight kind of heaving motion to them. That's just the recoil from the force production from pitching. That doesn't disrupt that stability landscape. It still retains the stable formation. We tried a range of different initial conditions. So the color here represents time. The Y positions are on the vertical axis. The X axis here are the X positions. We started around the equilibrium position, and for this whole range of initial conditions, over time they converge to the same location, right? So we see that it's insensitive to that initial condition. So that's great. But this is a potential flow solver, so maybe we're still missing something. What about an experiment that actually has this dynamic motion incorporated into it? So this sounds easy, but is a very challenging experiment. My student Pedro spent a lot of effort and time to kind of get these measurements going. What we have here is really a very unique facility. This is a one-of-a-kind facility where we have these free-floating platforms on dual-axis air-bearing stages. So there's air bearings in one dimension. You can't quite see them in this video, but there's some in the streamwise dimension. You can see some there. We have two of these platforms, and on board these platforms, we have all the actuation. We have the power supply, a battery on board. We have our compressed air on board for the air bearings. There are no electronic cables. There's no tubing coming off of these to add any external forces to these platforms. We have to be very careful about precision leveling these, about counterbending the rails, about perfect alignment between the rails. Any small misalignments, any small amounts of bending can actually lead to external forces that act on these platforms and generate artificial minima that are not what we want to see. So it takes a lot of time and care to get this up and running, but Pedro's done an excellent job, and he's done a fantastic job getting this up and running. So here I'll show you a video from one of these experiments. So in this video, we're looking from below here, and you can see there's Pedro's hand there, getting the experiment up and running. So he's setting it up in kind of an initial arrangement. So these are the two foils. There's an imposed flow from our flow channel that goes downward in this case. And so here he's going to let the system evolve. And so you can see that over time, you can see here that these two are starting to align. You can see in the side view here and starting to line up in the bottom view there. They have that out of phase pitching behavior here. And indeed, they line up into this side-by-side arrangement at some location along the air bearing stage. So he's going to turn off the motion on the foils here. You can see they actually start to go backwards a little bit because of the imposed flow. They're being dragged backwards, and then he resets them to some different initial arrangement. And begins their motion again. And lets the system evolve again. So they end up in another side-by-side arrangement. And we've looked at this over time, done many measurements like this, and ended up that they fall into this arrangement. They do this at different locations along in the two-dimensional space that they're free to move. So we know this isn't an artificial minimum. It just kind of keeps going to that. That's not what's happening here. So they end up in different points. But the relative spacing between them is relatively fixed. There's a kind of a tight distribution here. And this is actually some of the data that we've gathered on that. So we see that we do achieve this side-by-side equilibrium just as we had expected. This is really shown not only in the simulations, but in the actual experiments here. And in fact, we have to crank up the flow speed in the channel in order to get this to work. And we knew that that would be the case because in our simulations, we see they swim faster when they swim in this stable formation. And so we increased the flow speed in the channel 15% in order to get this to happen. So that means the two were swimming 15% faster than they would in isolation. So there is a hydrodynamic benefit actually happening in this particular formation. So we want to know more about what the performance landscape looks like and whether we can understand how to or where these high performance zones will coincide with stable formations. So we can take a look back to the original constrained data set and look at the performance measurements that we gathered from that. So here's a contour map of this collective thrust, and this is a contour map for collective efficiency. Over here, we've labeled this with the kind of stable points, at least in the near field here. And so if we look at the thrust here, this is our stable point that we've been looking at, this side-by-side arrangement. We see that here there is a significant thrust benefit, which is translating into the speed benefit that we're seeing when they're free swimming. And we see there's another high thrust zone here kind of in the wake zone, and that's another interesting high performance location. If we look at efficiency here, we see that for the stable side-by-side formation, there's a small efficiency benefit. But over here in the wake, there's a very large efficiency benefit. And so that's a really interesting zone when we're really thinking about maximizing performance. We definitely want to go there. But there's two things here that we really need to understand better. One thing is we need to understand what are the physics really kind of behind these equilibrium, these two-dimensional equilibrium positions. And then ultimately, can we play with the physics to kind of push these equilibrium into these high efficiency zones? And so that's kind of where we're trying to head with this. So we'll start off by looking at that first question. What's the physics behind these 2D stable equilibria? And what are some scaling laws that can describe this? So we use our simulations in this case where we do these kind of out-of-phase simulations, and we fix the positions here, and we vary the separation distance between the two and measure the lift. We can do a classic force decomposition from von Karman and Sears and decompose this into the quasi-steady lift, the added mass lift, and the wake-induced lift. The quasi-steady lift is the lift that you feel when there's no wake present. The added mass lift is the lift from the added mass forces. And the wake-induced lift is the lift that's induced by the presence of the wake. So here's what some of that data looks like. If this is the lift coefficient on the vertical axis and the separation distance between the foils here, the triangles here are the total lift. We see that when the foils have a large separation between them, there's a slight negative lift. This is the force that's pulling the foils together. We see that as they get close, the lift turns positive and it pushes them apart. And there's the equilibrium position between the two. Now, when we decompose into these fundamental components, the added mass lift are the black circles here, and that's precisely 0. And so the added mass lift plays no role in the equilibrium altitudes. And in fact, it's always a balance between positive wake-induced lift and negative quasi-steady lift. So this really is giving rise to these stable equilibrium points. And we can use this information. We've dug into this in a paper that we've actually are just submitting yesterday. I think it was yesterday. I'm not sure. I would love, I could share this with anybody who's really interested in a lot of the details. But we can learn more and kind of dig into these individual components and then build scaling laws from those. And so there are 3 components that I mentioned, but there's only time to really go through one component. So I'm going to talk about the quasi-steady lift. I think it's kind of interesting case in particular. So in our simulations, we can actually simulate the quasi-steady lift by running simulations without wake shedding actually happening. And so this is a set of simulations where we're looking at the time varying quasi-steady lift. The solid lines here represent what what we got from our simulations at different separation distances between the foil. And we can actually model this using kind of classic Kutta-Joukowski theorem, which is fantastic. So we can write down the classic Kutta-Joukowski theorem in a dimensionless form. So this is the quasi-steady lift. And the classic Kutta-Joukowski would, when you non-dimensionalize it, you wouldn't have this U star or this beta. But since we have two foils interacting together, there is these additional kind of pieces arise. So I'll explain the different components here. So this gamma star is a dimensionless circulation. This is the bound circulation for a foil if it was infinitely far apart from the other foil. The U star is the effective flow speed, dimensionless effective flow speed. So this flow speed is different from U infinity because when you have a foil that's close to another foil, its bound vorticity induces a flow at the leading edge of the other foil, and that alters the effective flow incoming to that first foil. And so this can either be additive or subtractive from U infinity. And beta represents a circulation enhancement factor. So again, when you have this bound vorticity from a second foil inducing a flow over the first foil, in order for the Kutta condition to be preserved in the first foil, the circulation bound to the first foil has to be enhanced in order for that to happen. And so this gives rise to a circulation enhancement as well. And we can use precisely this formula and calculate using the Kutta-Joukowski theorem the quasi-steady lift, and we get the circles that you see here lines up perfectly with our simulations, which is using the unsteady Bernoulli equation to do the calculation. So we know that we get precisely the right result. What's interesting is if we look at these individual components here for quasi-steady lift, this would be, if you're out of ground effect and you're just symmetrically flapping, this would be the lift that the quasi-steady lift you would generate. In the time average, this time averages to 0, as you would expect. If we introduce the circulation amplification factor, the time average is still 0, but the peaks get larger, or the magnitude of the peaks gets larger. And it's really this effective flow velocity piece that gets added that adds this asymmetry to produce the negative quasi-steady lift. And so what this is doing is that when these two are flapping close together, like at this time here, the flow that's being induced on the first foil is actually lowering the effective flow velocity. And so that reduces the lift magnitude. And so you get less lift on the positive lift side. On the negative lift side, when these are separating apart, you induce a flow to accelerate the free stream. And so you have a larger effective flow velocity and an enhancement in the magnitude of lift. It just turns out that that lift is negative. So you're enhancing the negative lift, and it becomes, over the whole cycle, a net negative lift that's generated there. So this flow-induced bound vorticity from the second foil and the first, really the effective flow velocity is what's leading to this asymmetry in the net negative lift. And so we can use this information to actually build simple scaling models to calculate the quasi-steady lift. So we can write down a simple formula based on those ideas. This is the circulation amplification factor. B is just the location of the bound vortex on the second foil, which is roughly half chord or so. And these are kinematic variables that come from the motion. And D star is the separation distance. So we can compare this simple scaling law to our simulations for quasi-steady lift, and we get really perfect agreement with all of our simulations if we compare our scaling law to the actual quasi-steady lift. An interesting side note here is that we can look at the case where we have two static foils that are side by side with each other. And this is exactly the problem of classic ground effect. And we can come up with a very simple expression for classic ground effect. And the first term is due to circulation enhancement. An enhancement in the lift slope is occurring because of this beta factor. And the second term is due to that effective flow velocity. And so with just two simple terms, we can capture classic steady ground effect within 10% error, which is quite amazing. And I will say in this case particularly, we had some actual experimental data, which is the squares here, and that also lines up perfectly well with that. So a very simple expression and a very easy understanding for classic ground effect. Kind of a side note, but kind of fun too. So I had to mention that. For the wake-induced lift, it looks very similar to this, but I won't go through all the details. But essentially, you account for the shed vortices in the wake, and you can come up with two terms associated with the wake-induced lift. Here, we don't get as good of a collapse for the quasi-steady lift. In fact, the cases that are a bit far off are the cases where the Strual number is greater than 0.45, which is where awake instability sets in, and we don't have that accounted for in our scaling laws. So we didn't expect that to necessarily be good, and it turned out not to be very good cases in particular. We can combine those two pieces and write out the kind of balance between quasi-steady lift and wake-induced lift to predict the equilibrium altitude. And it does bad for those cases where we don't have the physics introduced, so we didn't expect those to work. But for all the cases where there isn't that wake instability, we get a good collapse of the data, showing that our prediction is a good prediction within 20% error, are the dashed lines here, with the actual equilibrium altitudes. So we have a model that captures this quite well for Strual numbers up to 0.45. So one question we had from this is, great, like we understand the basic physics here, but do these stable equilibria even extend beyond 2 swimmers? Can we see this for larger schools? So we started to take a closer look at this. So here's an example where we had 3 swimmers, and I love this simulation. So in this simulation, you see the 3 swimmers here. We just tried this out at first. You can see that the interior swimmer here is actually starting to swim ahead of the other 2 swimmers. And you can see that going from one swimmer to the next, these are out of phase with each other. And you can see that the simulation blows up, right? It's a fantastic video. We don't normally show simulations that crash, but this is a great crashing video. So I love to show that. So it didn't work, right? So what happened here? What's going on? So we observed that the interior swimmer was moving out in front of the exterior swimmers. And that tells us, and that we hypothesized, that must mean that it's generating more thrust than the exterior swimmers. So we can try to balance the thrust so that it doesn't get kicked out in front of the other swimmers. And we can do this in many ways. And we chose to apply amplitude control. So the idea here is that we can take the exterior swimmers and we can increase their amplitude and potentially balance the thrust between the interior and exterior swimmers and then achieve an equilibrium state. We decided amplitude control was the better way to go because we can maintain frequency matching and synchronization. And so there's better chance of better performance metrics if that's the case. This also offers an opportunity to create tailored equilibrium states, which I'll talk a bit more in a second. But let's take a look at this simulation now. So we run this simulation where we've now increased the amplitude of the exterior swimmers and only about 3%. But there's a range we can actually increase it over. Doesn't have to be perfectly 3%, but in the 3 to 5% range, we can actually get this school to stabilize. So we can balance the thrusts here, and the school, this is the long-term trend over 200 cycles, and you see no crashes that are happening in those simulations. And in fact, they achieve this kind of dynamic limit cycle type of behavior where they're kind of oscillating around in a predictable type of pattern with each other. Some they're bouncing a little bit closer, a little bit further, a little bit back and forth. And you can see that in just the velocity data that you see here. So this does work as a way to kind of stabilize these schools. And in fact, we've done simulations of this. I don't have a video to show you, but we've done this up to 8 swimmers, and we can use this strategy effectively up to 8 swimmers. So as far as we know, this works for any number of swimmers in this side-by-side formation. For these 3 swimmers here, we're getting a small speed improvement, a 10% speed improvement for these 3 foils. So that's good. We're looking at how that speed improvement scales as we scale the number of swimmers upward. But we also know that this isn't the most amazing performance configuration or formation. We know that that wake arrangement seems to be much better. So we're really interested in that as well. So let's take a closer look back at that case. We're interested in looking at this kind of wake zone interaction case. And in particular, we don't have a 2D stable point there. We have a 1D stable point. So we're going to look at one-dimensional stability to start with. And I won't show you anything, but we're starting to have some thoughts about how to make this become a 2-dimensional stable point. So the first question is, again, this was fixed constrained data. If we do dynamic simulations, does this 1D stability show up? And if so, can we then tailor it using amplitude control, for instance, to kind of push this point into the high efficiency zone? So here's a simulation of two swimmers. So these are constrained, so they can't move laterally. And we know if they do, they're going to get kicked off to one side or the other. So we're only looking at 1 degree of freedom motion in this case, so, and looking at stability in just the streamwise dimension. So the follower, as it gets closer, it gets pushed away from the leader. And these particularly, this is for one kind of fixed phase relationship and one set of amplitudes. But we could start this at a bunch of different initial conditions. This represents the gap distance between the foils, normalized by the chord, so dimensionless gap distance. And this represents the time. And we see that if we start the foils in different arrangements, the follower settles out to some distance behind the leader. And there's actually a multiplicity of solutions here. So there are stable positions and they keep repeating. And it's about 1 wake wavelength behind as you go downstream again and again. So we see these stable formations, but how efficient are we here? And we actually had some constrained foil data, a second kind of data set here. And so the contour map is this constrained foil experimental data. This is showing the gap distance between the swimmers. Here we actually, on the vertical axis, we actually varied the phase relationship. So we have in phase, we have out of phase, we have phases in between. And we're plotting the normalized efficiencies here. The kind of dots here represent the peak efficiencies at each kind of gap distance. And so you could see that there's a clear place you want to be in terms of the gap distance and for a specific phase relationship in order to maximize the efficiency. For our free swimming simulations, they fell on these squares here in this performance map. And so they're getting an efficiency benefit, but it's not the best. We're not in the really high efficiency zone there. And ideally, we do want to be in the high efficiency zone. So we think that if we can actually increase the amplitude of the leader, this will, or decrease the amplitude of the follower, this will push the follower into this high efficiency zone because this efficiency map looks a lot like the thrust map. And at this point here, in order for the thrust of the follower to go up onto the high thrust peaks, the thrusts ultimately would need to be balanced. And the way to do that is to increase the amplitude of the leader or decrease the amplitude of the follower. So we've done that. We ran some simulations where we increased the amplitude of the leader. And if we increase that amplitude ratio, we go from the white to the light gray to the dark gray here. So we actually do push up onto this high efficiency ridge. And here we're actually looking at this normalized efficiency. And we see the white curves are the efficiency when they have the same amplitude. So we can get up to a 20% benefit. But as we increase that amplitude of the leader, we can push it into the high efficiency zone. We can go up to about 30% over here. And there's some other cases that we just got some experimental data on to go with this that show up to 70 or 80% benefits here in terms of efficiency. So you can really push to the high efficiency zones and tailor these equilibrium formations to generate really efficient arrangements. So that's all the major things I wanted to show you. We are looking at how we can extend this. This was all hydrofoils, but how does this extend to real kind of biorobots? And this video never likes to play for me. There's something happening. Yep, there it goes. He's got to help it along a little bit, give it a little push. So we are working with Hillary's team from UVA, taking their Tunabots, and then we have kind of a representative version of their Tunabots, and we're putting them on our stability platforms. And we're starting to look at whether these stable arrangements actually persist to actual biorobots, and what the performance actually looks like there, and whether we can apply some of these strategies like amplitude control to tailor those arrangements and achieve higher performance stable arrangements. This is what we're kind of moving towards right now. And we're also talking with George about whether we can do this with fish at all. And so he has these nice fish foil experiments where the fish will swim with these flapping foils. And so you can generate well-known wakes from the flapping foils and do test out very testable hypotheses with an individual fish and see how they respond to that. So it's very cool experiments, and they're getting some cool data on that. So we hope to answer some questions with those experiments as well. So Overall, what I showed you is this kind of seminal result from George's team that fish really do save energy while schooling, that there are these side-by-side arrangements, at least for hydrofoils, that are two-dimensionally stable. They can boost the swimming speed, a slight boost in efficiency. These really exist because of this balance between wake-induced forces and quasi-steady forces, and we've developed simple scaling laws to describe those physics. I've shown you that amplitude control can be a way to help create stable formations or stabilize formations, and can be used to actually push the high efficiency zones, or to push stable formations into high efficiency zones and make those coincident. So that's what I have for you today. With that, are there any questions?
Thank you. Yeah, it's really fascinating results. And well, it's only the first year for Murray. And so you always keep thinking about what's going to happen in the remaining 4 years.
I know. I'm excited to see what happens.
Yeah, okay. So I was thinking about the bigger picture, and at the beginning as a motivation for this set of Murray, you said, for 2x2, I mean 2 side by side, like people studied that, and for 3D and the schoolhouse. So then, okay, you showed very nice, elegant results about ground effect analogy. So I was thinking, well, if we're going from there to, let's see, arrays of those things, and a simple way to think about that is something in a channel, then basically mirror images, okay, just go to infinite dual direction. So I guess your elegant formulation can, with some modification, can still work. But but then okay, but then you showed immediately there are 3, but they are not just like that, right? So so that's a really nice twist. Yeah. So what's your? Yeah.
I'll add a comment to that too.
Yes,
I'll say that there's a slight difference when, I mean, yes, you could do kind of a mirror imaging effect and kind of think about an infinite number of swimmers like that. But when you have a finite number of swimmers, but more than 2, you start to introduce really interesting edge effects on the school. So when you start to increase the number of swimmers in that kind of side-by-side arrangement, the interior swimmers, as we saw in that simulation, were producing more thrust. But you can look at their efficiency levels too. They're different, and they're qualitatively different. If you actually compare the exterior swimmers, even as we scale to 8, 9, 10, the outside two layers of swimmers have characteristically different performance than the interior swimmers. And so that's really kind of changing the game, and why we need to use amplitude control there, but something you wouldn't see in kind of the infinite school solution, right? That's the edge effects go away in that kind of solution. Yeah.
Okay. Yeah. So it's really nice. Yeah.
Yes. Thank you. Yes.
Lots of great work. I appreciate your talk. I'm interested in that beta value that you introduced in your lift coefficient. So I did something similar actually recently with discs settling and their rotational induced lift.
Yes.
And I was curious how you are finding the beta coefficient. Is it constant for a lot of different scenarios, or is it very case independent?
It is only a function of the separation distance between the foils. And it is amazing at how well that works. So we considered, both in the, let's see if I could go back here a little bit. We considered, it's going to take too long. So we considered in our formula, in the bound circulation, you actually have the rotational term that you're describing, the rotational lift term, and the kind of steady quasi-static lift term there too. Those, if you have different theta dot values or different theta values, it doesn't change the circulation amplification vector for this problem. And it's amazing. We actually looked at this compared to, we did a paper with Peter Badu, and he did this exact solution for ground effect. So he did an analytic solution using prime functions and math that's beyond me, but he did a fantastic job with it. In those exact solutions, he saw precisely the same thing, that the circulation, not the lift, but the circulation would only be a function of the separation distance, in that case with the ground plane. And we saw that to be the case in our data as well. And in fact, when we use that, no matter which data we looked at, no matter how close, or sorry, no matter what kind of kinematic variables we use for Struhal reduced frequency, varying the ratios of the theta and theta dot term, didn't matter. We always get the same circulation amplification function. It didn't matter even when the pitching foil was at a different part of its stroke. If it was at the bottom of the stroke, closer to the other foil, or further from the foil, we saw the same circulation amplification on the positive peaks of the circulation curve and the negative peaks. And so for this problem, it's way very nicely simple so that it's not a function of the theta dot term and only a function of the separation distance.
I guess a follow-up question, have you seen other work that introduces that type of amplification term, or did you guys just?
No, we knew that there was going to be something like that happening, and we knew why it was arising. We knew that it had to do with the bound circulation from the second foil there. Really, when you think about that inducing a flow on the first foil, right, something has to change in the flow around that foil to make sure that the no penetration condition or the cut condition, if you want to think of it at the flow at the trailing edge, that those things are still preserved. And so something has to happen. That thing that happens is that the circulation gets enhanced. And so that's just back from kind of a classic idea from like von Karman and Sears in 1938. That kind of idea started there, I would say. Yeah.
Thank you.
Yep. No problem.
I have several, so.
Please.
So a couple are just clarifying, because you may have said it, but when you talked about when you started messing around with changing the amplitude to try to force things to be stable. So when you had the 3 in line and you gave the outer 2 30% higher amplitude.
Yep.
So you did that. And then so when you went up to like 7 or 8, it's always just the outer 2 that you're increasing the amplitude, and all the interior ones are the original amplitude?
That's a good question.
Because when you answered Leanne, you're talking about like usually it's 2 layers that you have.
This is true.
The effect.
This is true. I don't know the precise answer to that because I haven't checked with my research scientist about what that result actually is in terms of that question. My guess is that it is the outer 2 and that there's probably a little bit higher amplitude on the outer one, and the next one in is a little bit less, and then probably after that it doesn't matter.
Okay. But there's probably some easy, either linear or something drop off.
Yeah.
Or I guess like
I would guess, but I should really check the precise answer on that. But
okay,
yeah,
but there's probably a rule of thumb or a scaling that you could come to pretty quick that would just resolve itself over a couple layers.
I think so.
So the other big question, again, like I said, many questions, but so you created the force map to begin with off one swimmer.
Well, 2 swimmers interacting. Is that what you mean?
Well, no, but the original map you drew was that essentially what is
the position for the one swimmer? Yeah.
Right. So yeah, and kind of just going at where you sort of end up. You know, so you think about you put when you started doing tandem, or I guess they're inline swimmers.
Yep.
You know, you kept them directly in line because they would be an unstable in the transverse direction if they fell off the inline inline line.
Yep.
But if you start putting 2 upstream swimmers that are both generating equal and opposite force maps behind them, there would be a stable point in a staggered configuration. So have you started looking at those yet?
Yes, we are looking at that precisely. And for that same reason, we thought that might introduce a stable point there, that essentially the two force maps would balance. I don't know that that's actually the answer.
Okay.
What we've seen in preliminary data is it doesn't seem like that's the answer.
Okay. Because the broader question is like that first map was drawn just from what goes on around one swimmer. Where would you want to place the second? But that actual force map would start changing if you start with 2 and start talking about where to place the third.
Yes.
Okay.
Sure. Yes, and that's exactly the measurements Pedro is currently doing. And so I don't have an answer completely yet, but the preliminary data suggests that at least where we thought the stable point would be is not the case, but it might actually be closer, but we don't have all the data. So I don't know, but it's exactly our thought too. So, yep.
Any other last questions? Yeah.
Yes.
I have a question about your efficiency estimate, right?
Yeah.
So when talking about efficiency, you always use a single number, but in reality, for fish schooling, each individual's efficiency could be very different, depends on the spatial location. So, can you comment on, when George did his measurements, I suppose it's kind of average efficiency of all fishes in the tank, and
Yes.
when you do the
So-
analysis, and depends on where the fish is positioned, then
Yeah.
how that changes the picture of efficiency.
Yes, that's a good question. So first off, I would say, to be precise, George doesn't measure efficiency. What he measures is energy consumption.
Mhm.
And so what he's measuring in his fish measurements is the total energy consumption of the whole school. And so in that sense, it's kind of, if you wanted to look at it per fish, it would be kind of an average energy consumption per fish. And so the idea would be he had 8 fish in that tank, right? And that curve for the school was about half the energy spent to swim as 8 swimmers together rather than one by itself. But really, it's a comparison of 8 swimmers together or 8 swimmers by themselves, right? That's the best way to really think of it. In 8 separate tanks, kind of, or very, very far away from each other, right? And that would be kind of the idea. So the idea is that if you're swimming together as a group, you're going to save more energy. But there's should be kind of a distribution, like maybe the swimmers in the back are going to get a better energetic advantage. Maybe they save, even 1/4, maybe they only spend 1/4 of the energy to swim, and the ones in front are doing most of the work. So it might be heterogeneously distributed in terms of the kind of energy benefits. And so might be the ones on the edge are doing that too. Yeah. So it can totally depend. It can depend upon your synchronization. The edge can be better or it could be worse, and the front or the back. And so the placement in the school plays a large role and may also end up, if you think about like the edge swimmers, if you always do better or always worse on the edge, maybe there's a specific shape of the school that would really optimize energy consumption.
Right. In birds flocking, right? You see the people saying the leading birds, they take turns to take the lead, and does the same phenomenon happens in the fish schooling as well? Or?
It quite could. What we do know so far, so one of the major thrusts is on the biological side for George to understand what's happening in terms of fish swimming positions and kinematics and how those are linked to energy consumption, which is a huge ask. It's a lot to do, but he's up to the task. He can do a good job with that. So when he's tracking fish, what he knows so far is that the motions in the schools are very dynamic. So when we're thinking about robots, we're thinking about trying to do this in a fixed formation because we know that we can gain these really, in some ways, extraordinary benefits by doing so, and it's a much simpler prospect for control. But in the actual fish, they're kind of moving around everywhere. And so the question is, in a probabilistic sense, do these fish fall into a particular formation? Maybe like the V formation for birds, if the birds are kind of always rotating positions, but they're falling into this kind of typical arrangement that kind of comes out of it. And so we don't know what the answer is to that yet, but that's something we're going to be probing to see what's the kind of probability distribution function of where fish lie. And it could be that there's an underlying structure, or maybe it is just very random and they're just gaining a bunch of benefits from a bunch of mechanisms that average over the whole, time that they're schooling together that is good. So maybe it's a simple solution too. I don't know.
All right. Thank you very much.
Yeah.
I have a question about this first result that you presented. So when George was doing the experiment, there was not a particular organization that the fish kept, like for every flow velocity, they change patterns, right?
They did seem to constantly change patterns. It seemed like there was some structural things coming out of it, but I can't say too much definitively. Yeah.
And my other question was about the other results that you did in the water channel. Did you notice some type of boundary effect of the wall channel? Because I noticed in the video that you presented, the two fishes were kind of the same distance they were apart from each other. It was like the water channel.
Probably in the last video you were talking about with the actual robotic fish, is that what you're talking about, or the hydrofoils?
And the second video, just after the result that you present from George, like there were two hydrofoils.
Oh, yeah, from Hillary's team. You're talking about the
Yeah.
Tunabot robots
Yeah.
there. Yeah, their channel is pretty narrow, so I'm not quite sure what kind of boundary effects they're having there in particular.
Okay.
And so that's part of the reason why we're looking at doing those measurements in our channel, which is about 1 meter wide, and their channel is, I don't know if you remember, I want to say it's not 2 feet wide, it's less. It's like, I think it's 20 inches wide or so. So it's a little tricky. I agree. Like the wall effects there may be playing a role. And so a lot of the, what they're showing there, they're pretty preliminary, and we're not using them as results yet, but it is a concern that when you have a small channel to be worrying about those boundary effects. And so we're trying to think about these kind of more precise measurements in a more laterally expansive channel, so we don't have those boundary effects as being present.
Your cross section is pretty similar to the one in Lab 30, right? Or the one you were at this morning, right?
Yeah, so I think it's actually quite similar. I think yours is longer, and you have
Raphael's been having some questions for his upcoming PIV unrelated to this. Like, what does our boundary layer look like?
Yeah.
So that was some of his motivation. So maybe we could compare one day, once Raphael measures some of that.
Sure.
Did you have any other? Oh, go for it.
Oh.
Whoa. Hello. Okay, perfect. So this is a message from the Zoom. It's from a Chris Ellis. He asks, how did you choose your foil shape? Does the shape matter?
So shape definitely does matter. For bioinspired propulsion, there have been some studies in recent years that have looked at foil shapes on performance. That's always in an isolated swimmer. I have no clue about the effects and interactions at this stage. We tried to set our foil shape as being relatively standard. We started off using a teardrop airfoil, which is maybe standard in some unsteady propulsion studies, but not really beyond that. It's not a great steady flow airfoil. There would be typical separation. When you're doing a large scale kind of unsteady motions, some of those boundary layer effects don't really matter, and you're dominated by these shed vortex structures. So the details of the boundary layer most of the time don't play a big role. We moved to NACA 0012 though, just out of concerns of the kind of nice standard profiles. So we haven't done anything beyond NACA 0012s. That's where we're now kind of sticking with as our kind of typical foil. That is something to be opened up as a variable, but we already have enough variables as it is, and so it's a very tricky problem, as always. But shape does matter. It does make a difference on performance. We do know that from isolated foil studies. I don't know how those optimal shapes would be altered if we're talking about interactions.
I mean, I think it's worth pointing out that Radica's robots also, they look like they're just little rectangular flat plates that are the caudal fin.
They are. Yeah, they are particularly. Yep.
Yeah, so going way too far biomimetic is probably not a huge payoff at this point.
Yeah, at this point, there's a lot to learn, even with very simple, even if we just use flat plates, it would be still a lot to learn with just that. Yeah. And so we're I guess not at the stage to go down that route. Yeah.
And then, so I think we are at the close, but I had one simple question following on Raphael's, which is, so George used giant Danios.
One of the species he's used.
In his 8 in a tunnel.
Yes.
Do those usually school?
They do.
Okay. So it didn't look like they were the same thing that you showed us the inspiration video for earlier. But
I don't remember, but
so it was sort of predicated on that. Okay, so they're not really finding a normal shape in George's tunnel. Are they a species that would do that if there were more of them out in open water?
They do school together, as far as I understand. And we have 3 species that we're actually looking at on this project. The Danios are great because they're small. They fit into the smaller channels. That's the benefit for them, particularly. And you can fit more individuals into the school.
And some are cooperative.
And some are cooperative, yeah. And they're as far as what George says, they're relatively easy to take care of. They're not too challenging in that regard. We have larger species, trout, which you can't fit as many in the flow channels, but you can fit some of them in the flow channels, and they also school together, especially when they're doing their migrations. We also have tuna, and tuna are tricky because you have to have a special facility to work in those because they're big, right? They're not the small little fish that you get into the flow channels. So George has a collaboration with Greenfins over in Rhode Island, I believe is the place. They have a large tuna facility there. And so he can do measurements. The measurements are much more limited. You can't do these fancy respirometer measurements because you don't have a respirometer tank that large for tuna, but you can get other measurements, kinematics, look at the proximity and behaviors. So there are things to gain there, and it allows us to look at a range of Reynolds number scales for the actual fish. And allows us, he has ways to push the fish even in the Greenfins facility to swim fast. And that's really a kind of a key feature of the biological measurements, is that we've chosen strategies that really push the limits of the fish. We don't want the fish to just be milling around and kind of hanging out together. We want them to be actively swimming and pushing their kind of aerobic limits. And so that's why that tank goes up to 8 body lengths per second, which is about as fast as you can get the fish to swim. So we're really looking at pushing the fish to really understand the hydrodynamics of high-speed swimming.
Leanne, go ahead.
Yeah.
SAFL can easily make one.
Yeah, that's a great pitch because we have lots of large facility needs. So,
So let's see Leanne tied a bow on that with a shameless plug, which I appreciate. I want to thank everybody on Zoom and to Dr. Mord. Thank you very much for that talk. It was fantastic, and for everyone for the questions.
Yeah, thank you, everyone.